Hello everyone, thank you for coming to TyphoonCon online, and I hope that all of you are safe, staying home and doing great during this pandemic time. Today I would like to share with you our research that we prepared together with my colleague Alexey Kulaev about zero-day exploit chain that we found in the end of last year. So at first, a few words about myself. My name is Boris Larin, I'm a senior security researcher at Kaspersky Gray team. And I'm a reverse engineer. I like to analyze firmwares, kernels, find vulnerabilities, participate in bug bounties. And at work, my main focus is to find the zero days exploited in the vault, and I have found a few of them. And previously, I presented at a number of information security conferences. So in just 1 year, from May 2018 to May 2019, we have found 6 zero days. So all of them were used in different attacks, but there is one thing that is common for them. All of them were used in highly targeted attacks. But then we have found 2 more zero days. And at the end of October 2019, we have found that exploits are being delivered from a Korean language news website. A classical watering hole attack. All the visitors who visited this website they received these exploits. So here's how this website looked like. It's clear that it's for Korean language audience. And the attackers, they modified the mine index page with very small addition. You can see it on this slide. It just loads remote script from that pretends to be a very popular JavaScript library. And here's the contents of this script. It loads some another script that has name Charlie. And it performs initial verification for the target. It checks if user has a Windows operation system. It checks if it's 64-bit operation system, and it checks that user has a Chrome web browser. And after that, it gets some additional data from PHP script. So here's the retrieved data. There is a number of data chunks that will be downloaded, and also hex encoded URL and encryption key that will be used after exploitation. So after that, Charlie downloads a number of chunks, then joins them together and decrypts. And it results in a new script that gets executed. So this new script is an actual exploit that we are going to talk about today. And it was a really huge obfuscated script. It was huge because it contained a number of massive byte arrays. That was the WebAssembly module that was used at later stages of exploitation. And there was also shellcode and portable executable file. And right on start, this exploit it was performing some additional checks for Chrome version. It was targeting only Chrome version 76 and 77, but we found out that version 78, which was the latest, it was also vulnerable. And as soon as we realized this, we shared this information with Google Chrome security team, and they assigned a CV number and fixed this vulnerability. This vulnerability it was used after free in audio. It was possible to trigger it due to race condition between renderer and audio threads. And here you can see the link that this commit that fixes this vulnerability, and also an official comment from developer. So the problem was that before the patch, it was possible to nullify buffer inside reverb object. And basically there was just no proper locking between audio and the renderer threads. So we were able to fully reverse engineer this exploit. Originally all the names and contents were obfuscated, but we were able to deobfuscate it and recover all the logic of exploitation. So let's walk through all the stages of exploitation. At first, I've got to say that exploit writer has a perfect knowledge about Chrome internals, and especially about partition alloc allocator. You can see that exploit has a number of primitives for getting important allocator-related data, such as superpage address, partition page address, the index of used partition page, and the address of partition page metadata. And at first, the code initiates offline audio contacts and creates a huge number of ear filter node objects. They are initialized via two float arrays. And at this stage, exploit begins initial exploitation and tries to trigger use of the free bug. So for this, it creates objects for a web component. It creates offline audio contacts object. It creates two convolver node objects. One of them is used to start audio processing, and another one is audio buffer for audio channel. And this function, trigger UF, it's executed recursively. What it does, it fills audio buffer channel with zeros and starts rendering offline. At the same time, it runs a loop that resets the channel buffer and tries to trigger the bug. And exploit uses a later function to simulate the sleep function that is present in the operation system to suspend current thread and let render audio and audio threads to finish execution right on time. And the exploit, it checks that channel buffer contains any data that is different from previously set zeros. And if it's the case, it will mean that use of the free bug was successfully triggered. And at this stage, this buffer should contain some leaked pointer. And so partition alloc, memory allocator, it has a special memory, it has special exploit mitigation that works like this. When some buffer is freed, its pointer is byte swapped and added to free list structure. And when later some code will try to free this buffer, it will cause a crash of process. And he can see that exploit, it performs some checks, it byte swaps this pointer, leaked pointer, and performs some heuristic checks to see if it's an actual pointer. And this way it bypasses this mitigation. And this leaked pointer is used to get address of superpage structure and verify it. And then it's passed to the function that is present on this slide. So it's used to get a rough pointer to freed forward array, which has type audio array doubled, and it's present in the ear process object that was created by ear filter node. Here you can see that exploit, it calculates page index delta by checking the version of Chrome, because these are sets they are hard-coded for different versions. And the vulnerability, it's actually triggered not once but twice. After the address of the right object is acquired, vulnerability is exploited again, but this time the leaked pointer is sprayed inside of one of the larger audio buffer channels. This time two such objects is created. And this time exploit uses function getFrequencyResponse to check if exploitation was successful. The function creates an array of frequencies that are filled with Nyquist filter, and source array for this operation is filled with zeros. So if resulting array contains a number that is different from number of p, it will mean that exploitation was successful. And after that, exploit stops recursion and executes the function that you can see on this slide. It's used to allocate the audio channel buffer again and reclaim previously freed memory. It also prevents the possible crashes by repairing the heap, and it does that by allocation of various objects of different sizes and performing heap defragmentation. And it also creates a big wind array that is used to create arbitrary read and write primitives. So heap defragmentation is performed with multiple calls to the improvised collect garbage function. You can see it on this slide. It creates a huge array buffer in a loop. And exploit manipulates partition page metadata of the freed object to achieve the following behavior. If the address of some another object is written to big wind at index 0, and then a new 8-byte length object created, the value located in the index 0 is read back, and the value located by previously set address, it will be read instead. And if in case something written at index 0, then this value will be written to previously set address. And after achieving arbitrary read and write primitives, comes the time to get code execution. And to do that, WebAssembly functionality is exploited, and the previously mentioned WebAssembly module is used. So in Google Chrome, currently memory pages for WebAssembly just-in-time compiled code, they are located with read, write, and execute permissions. So in case you're able to get pointer to such page, you are able to overwrite it with shellcode. And here you can see the code that was located inside this WebAssembly module. You can see that basically just performs some dummy logic. It just increments some local variables. And well, exploit writer, it just needed to have a really huge WebAssembly model to allocate enough space for shellcode. And our WebAssembly model, it's executed with file reader object, and it creates file reader loader objects internally. And in case if you are able to parse partition alloc allocator structures and you know the size of the object that will be created, you are able to predict at what address this object will be created. And in case, well, when you get it, you are able to parse it, and you are able to get the address of just-in-time compiled code from file reader structure. And on this slide, you can see how this address is retrieved from file reader object. And then it exploit just overwrites it with shellcode and executes it. So once again, like all the variables, all the names in exploit, they were obfuscated, but we were able to figure out what is located where just by ourselves during analysis. And let's talk about shellcode that was used in exploitation. Well, it's quite simply portable executable loader. It just loads executable that also located nearby in script in another byte array. And this portable module, it mostly consisted of the code to escape sandbox by exploiting Win2K driver for elevation of privilege. And code exploit was written to support the following versions of operating system: Windows 7 and some early builds of Windows 10. So let's talk about Win2K driver. This component has something of a bad reputation. It has been present since the oldest days of Windows, and according to Microsoft, it's responsible for more than 50% of all kernel security bugs. And Microsoft, they implemented a number of mitigations a few years ago aimed at complication of exploitation for Win2K vulnerabilities. In the last 2 years, we have found 5 0 days exploited in the wild that exploited Win2K vulnerabilities, but the majority of them targeted versions prior to the release of Windows 10 version 4. So, like seems efforts Microsoft put into these mitigations, they are really working. But I also need to mention that Google Chrome has a special security feature that is called WinZTK lockdown, and it eliminates the whole WinZTK attack surface by disabling access to WinZTK syscalls from inside of Google Chrome processors. But this feature is only present on machines that are running Windows 10. So I think it's fair to assume that this operation, it was targeting on the users running Windows 7. And let's talk about vulnerability. CV 2019-1458 is an arbitrary pointer dereference vulnerability. In WinZTK driver, there is a special syscall. It's called setWindowLongPointer, and it's related to a number of vulnerabilities in the past. So in WinZTK driver, there is a few important objects, windows, that are represented by tag-windy structure. Well, windows, they might be of different types, like there is a scroll bar window, menu window, list box, and etc. And in tag-windy window structure, there is a special field, it's called FNID, that is used to represent a type of class of window. And the different classes, they might also have a different extra data associated to it. Basically, just some another structure that is appended to the end of tag-windy structure. And quite often, such structures include some kernel pointers. And this is called, it can be used to overwrite this extra data. But of course, only after validation. But in this case, this validation, it was just insufficient. Here you can see the code that would have prevented this bug. But prior to the patch, the values for the check for FNID desktop, switch, and tooltips, they were just not initialized. And they were not initialized in this table, and rendering this check just useless and allowing kernel pointers inside extra data to be rewritten. So here's all the steps that are needed to trigger this vulnerability. First, you can use user message call function to call window procedure. If you provide a specific message ID and DB type, you will able to execute create message of switch window, and it just sets FNID equal to FNID switch. Then you can use vulnerable function setWindowLongPointer to set arbitrary pointers that will be treated as structure of switch window. And then you can call user message call again to trigger the reference of arbitrary pointer that you previously set. And there is a code path that increments and decrements some integers located by this structure, by this pointer. So exploitation. Exploitation is performed with bitmaps technique, and there are also two different kernel SLR bypass techniques. For Windows 10 and for Windows 7 and Windows 10 threshold 1 is used GDI shared handle table technique. Basically, just well, in older versions of Windows, there was a special table located in the user space that contained kernel addresses of all bitmaps. And this technique, it was fixed in Windows 10 Redstone 1. So for this version exploit uses a node technique. It creates accelerator table, then leak its address via G shared info handle table, which is also another user level accessible structure containing kernel addresses, and then freeze this accelerated table with known kernel address and allocates bitmap using the same freed memory. This technique was fixed in Redstone 2. And exploitation is performed with the use of surface technique, which was mitigated in Windows 10 Redstone 4. Well, bitmaps, they are represented by surface objects, and they have the following header, and taken notice on two important fields. One is the size of pixel data buffer, and another one is pointed to pixel data buffer. There exist special functions, API functions, set bitmap bits and get bitmap bits, and they just copy pixel data from kernel and into kernel. So in case you're able to write the size of pixel data and or the pointer to pixel data, you just achieve arbitrary read and write primitives. So this is what exploit does. It allocates 3 bitmaps. It leaks their addresses. It uses address of bitmap 1 to point to header of bitmap number 2. It uses vulnerability to increment size of pixel data buffer. And then it's able to perform out-of-point writes to write size and point to pixel data of bitmap number 3. So this way it achieves arbitrary read and write primitives. And exploit uses these primitives to parse the process structure and steal system token. Well, it's a very common technique. We see it in almost in all elevation privilege exploits. And kernel address of the process structure is retrieved using function in enum device drivers. Here is description of MSDN for this function. You can see that this description says that this function can be used to retrieve loaded addresses, kernel addresses of all drivers that are loaded. So yeah, this information is provided to user level. And exploit just parses enters kernel executable and searches for initial system process variable. And like enum device drivers, this technique still works even on the latest versions of Windows. And after achieving system privileges, module performs signature search in memory of a browser, and it downloads a GIF image that was packed previously before exploitation. And it's not really an image. It has a special payload appended to the end. And this payload is decrypted. And it results in another URL, which is it's also is not real Gpack. It's just XOR encrypted portable executable. And finally, it's get dropped to temporary folder and executed. This executable, it was Raj's fix package, and it would execute iohelper.exe. So all what this model would perform, like it was a persistent model. All what it would do was to create 5 tasks with following names. And you can see that all of them were created with different intervals. And there was only one of such executables present in RRSFX. So here's the logic of this executable. Well, no matter of its name, it's really an x86 executable. And it's just simply a stage downloader for the next stage. And it just downloads it, drops it on the disk, and it was intended to be executed by previously created tasks. And so here is how URLs for this next stage were generated. You can see that also computer name was passed in arguments. And actually, we had not a chance. We had no chance to take a look at this next stage because, well, our products, they protected our customers at, like they prevented exploitation. So this final stage was never downloaded. And when we tried to get it during analysis, we only received dummy responses. So yeah. So I want to say thank you to Google Chrome and Microsoft security teams for fixing these vulnerabilities so quickly. And Google was actually generous enough to offer a bug bounty for this video. And we rewarded this donation. We donated it to charity, and Google matched the donation. So yeah, basically this is it. Thank you for coming, and see you next time. Bye bye.